Okay, I wanted to do a quick video about um, post-processing of lattice Boltzmann results. So here I've imported a 3D lattice Boltzmann solution, and it's about 24 million cells. And so I can take a cut plane through that and look at, for example, the velocity. So this is just flow over a sphere, and it's using the bounce back method for the wall boundary. And as well as velocity, I've got turbulence, density, I've got something that marks whether the cell's alive, cut cell or dead. But most importantly, I've just introduced a distance field. So I can use that to create a contour surface. So if I delete that, then what I want to do is to get the contour surface. I need to cell data to point data. And that takes a few seconds to sort that out, but that's needed in order to plot contour surface. And because this is just a uniform Cartesian mesh, it hasn't got the surface, it's not a body fitted surface. So I select contour, and then by default it's gone to the LCD field, so that's a bit messy. So I change that to distance field, and that is set to a distance field value of 0. So if I change that, I could increase it a little bit or decrease it a bit, but 0 is the right one to be on. And so I can now display the solution on that surface. So, for example, the velocity, density is what I want. So now I'm having a look at the density on the surface. Now I want to integrate the pressure. So in order to do that, I need a calculator function, leave that on point data. I'm going to call that force, and then I want to integrate the rho divided by 3 and multiplied by surface normals. So that should integrate the pressure field, and we're going to call that force. And so the next thing to do is to integrate variables. So just so I can view that. Force. Yeah, so having integrated that, we've got there the force values in X, Y, and Z direction. So this is the value you're interested in, which is this value here. So having integrated that, then I can put it into my calculation. So this is the value that we've just attained, is that X force. Now I've calculated half rho v squared as this value here because rho is 1 at the inlet and the v is 0.04, so half rho v squared, get that value. The area, well, the mesh is scaled correctly, so the area, the sphere is a 1 unit diameter, so pi r squared I calculated as 0.785, so that is your frontal area for the sphere. And I did an area check in ParaView by clipping just half the sphere and then integrating the surface normals, and I also got that confirmed that the area is about right. So then I've got my force and I've got half rho v squared times area, which using those two values comes out at 0.0006. 283. And so then my calculation to find CD, the drag coefficient, is the x-force divided by all of this other stuff. And once you do that, you get a value of 0.396, or nearest damn it, 0.4. And so that is the first time that I've been able to get a sensible value from a lattice-Boltzmann solution, having tried momentum exchange method and also doing some Wake-Travis integration and just getting some ridiculous numbers out. But from this result, I'm getting a CD of 0.4, which seems a lot more sensible. So just to recap, I read in my full 3D flow solution, do cell data to point data, so that I can get a contour surface. And because I've got the distance field stored in the mesh, I can do a contour of the distance field to get the zero level surface. So that's what we're viewing here. Then I can look at the density on that surface and then use the calculator to get the pressure, which is rho divided by 3, and multiply that by the surface normals, and then integrate that. When I integrate that, we get the 3 force components, like so. And those force components can then be normalized by half rho v squared times area in order to get a drag coefficient. And so that's what I've done.